remedy based on remedy APIs, and gradually as they moved everybody to mid-tier, we added support to the mid-tier and migrated some of our technology and the things that we're doing to that layer. There are a number of things that I guess with starting to get more difficult to get things right. The user base is increasing. You have complexity of the systems, larger user base. Systems are changing more frequently than maybe a while back, because the users are more demanding in some ways. There is a number of possible configurations because of the complexity of the system. It's a multi-tier architecture, and then very rare to see out-of-the-box system. Even out-of-the-box systems, they need some tuning, and there's documents and documents on how to go about optimizing the system. But it's really a straightforward process, because while a set of configurations will work on one system, it might not be appropriate for another system. It's very much data dependent, it's very much configuration dependent, so it is always good to adopt the best practices, but to validate they actually work for you. So whether something works for a typical system, it doesn't. If something works for a typical system, doesn't necessarily mean it will work in real life in a system that you need to look at. So there are a number of approaches. There have been some attempts to basically define tests that would work all with the artificial data, and we come across that, but there's always a problem with that approach, simply because the performance of the system is very much data dependent. So you may get system is working perfectly until you apply your own data. As soon as you apply your own data, things change. So it is good practice to actually look at the system with the data that you expect to see there, with the configuration that actually you need to run on, rather than populating systems with artificial data and try to guess what would happen when you actually apply your own data. Now, to start with, normally you need to define your objectives, when things are going to happen, which environment is going to be tested, assumptions about what you would be measured, what is the minimum and optimal testing set, and expected outcomes. Now, very briefly there, I have been testing various remedy systems over the years, and we kind of adopted an approach where if the whole process, if the single testing cycle needs to take more than 5 days, we're probably overcomplicating definitions. So initial testing cycle needs to be brief. You need to keep it simple and very straightforward, because you need to get the results very quickly. Later on you can add complexity to there, so it's good to state objectives, and you can, even if you have a day, sometimes you would decision whether to validate something or not, whether to test something or not, depends on the time available. And then it's a very different if you expect something to take a couple of months, or if something is the whole testing cycle can be completed in a week, or even if you have very little time, or you need to repeat those very often, you can define something that would be achievable within a day. That means that you can run, you are more flexible in how you going through the process. So, different approaches. Standard approach and very still common approach is to go through the whole process of actually it's first the requirements definition and gathering, and then defining what the hardware requirements are, assigning that, purchasing hardware, going through the process of deploying, trying to optimize, use whatever documentation is available to do that, apply the data, and only then the real testing starts, if you still have time. Now, very often in that scenario, the last step just before the launch is squeezed. Things don't always go to plan, and then as you start running out of time, that launch date is closer and closer. And one thing that gets very squeezed is the last loop in there, and that's testing. Now, that also means that you sometimes get results when they won't make any difference. If you last stage, you find that, well, there's a little bit of work, there might be need for some more work in a particular tier or in a particular application. It's too late. There's no time to address that. So testing it becomes well, it becomes almost, well, just whether we are safe to launch or it's just too risky to launch. So the systems will very often go in production not really ready, and that's very often simply because there is no that constant check during the process. Much better approach, not always easy to change the way of thinking, is to do a quick validation at each stage. So as soon as you deploy, you run a check. You always have the data may not be there, you check. You modify something, you add the data, you check the system. You start optimizing, you check. You keep on checking all the things that you need. It means that you can focus on things that really make a difference, rather than trying to work from very generic list of what may or may not be relevant on the system. That means closer you get to the launch, to the go live date, more and more information you have about what is actually happening with the system, how it behaves. You probably already went through a number of things that may need to be addressed. Rarely you will see there would be a system that as soon as you deploy it works. I have never seen one. Very often it's not too well. It's not too hard to resolve things, provided you get information about what is happening early enough. The worst situation is when you know that something is wrong, you know that it can be resolved, but you don't have time because the results are coming very late. So better approach is to take that iterative approach and for that to happen, you need to start simple. Start with a test that are not overcomplicating your validation or checks. So keep that simple, because even the simplest transactions will produce valid and valuable results. You would be able to repeat them more often, they will run shorter, and you can gradually increase the complexity as you get more confidence with the system. So you get more detailed results when you resolve some of the earlier issues. You don't try to run very thorough testing on a system that, well, it's almost irrelevant, because if the system doesn't perform, no use running 15 different tests to tell you that the system doesn't run. First test is enough to give you that information. Now, the other thing with that means that because you continue to run this in iteration, it's much easier to compare what the changes are. You will know where problems are coming. You will generate reports much easier, and they would be much better understood and related to the system that sits underneath. You also get results when you need them. And as I said, problem analysis resolution is much easier if you test changes rather than test the system after it's been completely set and configured, because then if something is not quite right, it can be quite challenging to find out where things are going wrong. We've done one and the other. I mean, sometimes you have no choice, but you have to go for the test at the end. But as I said, there are a lot of benefits, especially when in the process when you're trying to optimize your system, when you try to tweak the system to validate what the effect of certain modification and configurations are. Now, As I said, in order to do that, in order to be able to go through the whole process, and I said, well, if you need to validate some simple change on the system, you don't want to test from the moment you need to build a test to the moment you get some results. You don't want that to take more than a day. You need to be able to run simple tests within a day, and so that can be repeated often enough, because normally systems will change, data will change, configuration change, which means that you will need to go through the whole process of creating, validating your test itself, running it and producing results. So creating a very complex load model means that you will spend more time trying to build your test than analyzing the system, which means that it will not be practical, and then you don't get results from that. So it's much better to start simple, because I very often use a very simple transaction. It can be as simple as user logging in and maybe loading one of the console, or loading one of the main consoles that they have access to. That would if you test only that transaction on your system, you will get a lot of information about what to expect, whether the system will stay up for a prolonged period of time, whether there are any memory leaks, they're relevant, how you need to configure mid-tier in order to combat some of the issues that might be related to that. So there is a value even with the simplest of simplest, in terms of simplest valid transaction that would go through the whole stack and do some meaningful work. So once you've done that, you get more confidence with the system. You can add complexity. You start widening what you look at in order to catch some things that you may not have seen initially. But by adding complexity gradually, you also know that if you are spotting something later on, where that is coming from. So you resolve first the main issues before looking for the next, because there is always a limit. It's just not trying to overcomplicate the analysis process. I said design for analysis. It also means that you define your test so that you interpret results much easier. Improve, calibrate, and validate the load models. It's a process. It's an iterative process that means that you gradually improve things. Also, by keeping things fairly simple and having some read-only transactions in your model, you can cross-reference. If you have already production, you can get a view of what is happening currently in production, so that you can estimate what the impact on the users would be with the new system. Whether they would accept certain levels, what you see throughout the day, whether you need to worry about that, and that can improve the model itself. Now, then you go to the process of creating a test. And I said we have put quite a lot of work. We moved some of our existing technologies, some of the Remedy API technologies, some knowledge about on that level, because mid-tier, when it was introduced, it was almost just a wrapper for what the Remedy API calls are. And since we handle Remedy API calls, and we could build a test automatically on the Remedy API calls, we moved some of that technology to support to the mid-tier, so that we present the data in a way that would be remedy specific. So we expose data that it's much easier to look at the dependency between different objects and transactions, so that it's more remedy-like tests rather than hiding remedy behind the protocol. There is just a carrier in that case. We also continue to improve the whole process of building the test, because very important thing is that you need to be in a position where you can create your test very quickly. Things change, smallest change, because it's a data-driven application, smaller change to the data may mean that you need to rebuild your tests, and you need to be able to do that quickly. So we put a lot of work in optimizing that test creation process, so that it shouldn't take more than half an hour to an hour to build a single typical user transaction with the system. Now, when you start executing, you baseline it, you start to get basic levels quantification of each user step. That becomes your measurement, and that, by repeating it in a subsequent test run, you have a direct comparison of what was happening before you apply some change on the system and after. You can also start with the worst case values. If you expect that the maximum number of incidents per hour is or per day is 300, worst case they will all happen in an hour. So you can start very aggressively, because initially you're just looking at this, well, how stable the system is, whether we will survive the load before you even try to optimize it and look and fine-tune the user load. It's not easy to express user load very accurately in terms of which transaction you need to do. They're not very predictable. So it's good to start with the worst cases. You focus on changes from one step to another, so it's much easier to compare results, because you always know what the change was, and if there are any degradation, you can easily often relate that to something that happened in the meantime. Then you go to, as I said, you go to the process: optimize, validate, and continue. So it's a constant process there. So result analysis, because of that, becomes a little bit easier. You can do before and after comparison. It's much easier to do that than to look at the complex system and start producing results. You have simplified result correlation. You may have something that will relate even to the production if you have that level of detail. The level of detail depends on the outcome. If the system is not staying stable, there's no point in running a lot of tests and trying to get a lot of detail, because you can recreate problems easily. Once you get things more stable, you can look at what is the worst part of that, so that you can focus any optimization effort on a component or on a tier that is relevant, rather than trying to blank optimize everything, because you may be spending effort when it may not be most effective. Dynamic load control to get most of the single test run. We also have, I mentioned, we have a way of running tests very interactively, so that you can, in a single test run, get a number of results that will validate what is happening. Some of the examples: this is one of the tests we run, and this is a single test run that run over a period of, well, maybe this is just half an hour or so. But in those half an hour, we can see already that as we increase gradually the load, that's the blue line, that's a user load that was increased. The response time, that's the black line, was increasing gradually, and then at some point it just started to serialize. So we can see that there's a serialization point at this level here, where any subsequent increase in the load will just queue up the users. You can get those results very quickly. What you can do at that point is start analyzing what is happening with the different transactions, break them down, see where the most of the time is spent, which is the fastest performing transaction, worst performing transaction, so that you can try to understand where is time spent. If your test is built to give you indication about the different layers, and you can define a test just to give you have a database heavy parts of the transactions. You may have transactions that even don't touch the database, some transactions that even don't go to the remedy server, but they stay on a web server. You can break down simply from measuring the user experience where time is spent and what you need to look at next. You can break that down in terms of figures or numbers that are later easily comparable to the next subsequent test runs. So it becomes, the whole process becomes much more streamlined. Now, I mentioned it's dynamic load. This is important there because it's the same example. We gradually increase the load, and that's again that blue line. The green line is that follows that is a throughput that we measure. So we can basically we say, well, we increase the load, and the number of transactions that are being completed is gradually increasing up to that point. So again, we have that curve where there is a limit of the number of transactions that the system can complete, but we continue. What is interesting here is that we need to check whether the system will stay up, whether it will go back to the levels that we were seeing before after it's been overloaded. It's probably one of the first things that even before you try to optimize the performance of the system, to make sure that it will stay up long enough. And it's not always easy. It's a thing. There are, I said, there's quite a lot of complexity in the way you may be pre-configured stack, but it's never pre-optimized stack. Your own deployment may have things that will mean that once the system is overloaded, something will fail, and you will not get back to the healthy system again. So being able to go through the whole process in a single run, and this run is maybe 2 hours. In 2 hours, we've got a scalability curve. We know how the system behaves. We know what the limit is, and we also know that it will recover if even if it's overloaded. You can also continue that over a period of the next couple of hours, running quite fast, to see whether there are any issues that are related to that. So at that point, we look at where the issues are coming from. Because we're repeating the process, issues are always, I would say always, related to the latest changes in the system, because as you modify something, you rerun something that you understand well. You know how it behaved before. You can understand what change is, and you can relate that to what you say. So that means that you can recreate the issues, if needed, expand the test, and then tune it, because you can recreate the issue. It's very easy to evaluate the effect of any optimization. Then, if needed, you can even probe additional interfaces, whether you go directly using the Air API to the remedy server, check whether that is healthy, whether it's behaving as you need to, database directly, or define additional tests that will tell you that. It's different approaches. Then you apply the changes, validate what the impact is. It's, as I said, it's never, there are guidelines, and there are maybe the garbage collection is a good example. Well, this configuration may work, but this configuration may also work, but you need to take into account that. Easiest way: apply the load, change the configuration, apply the load, compare the results. You will see if it works for you or not. You will see what will happen at the moment that it kicks in. You will see what happens when there's a stable load, whether the user experience will be affected. You will see at what you expect to be a peak load. There is no better way of understanding what impact of certain configuration is than actually measuring it. So much easier than guessing. There's a lot of guesswork otherwise. Now, what that means that is when you run a test, you may spot things, but as I said, because you can relate to something that is happening, it's a little bit easier to resolve them. Some of the examples there, one of the graphs, again, same sequence, gradually increasing the load, ramping up the load up to the point where we see the system starting, well, that transaction rate, or that green line, is evening out, which means the system has already reached the capacity of what it can complete. And then we look at the behavior. Here we just look at the stability. There is those black line peaks, means that what would normally be completed in less than 10 seconds occasionally may take up to 100. Indication that there is some contention, there is some locking on there, because things go up and down quite a lot, and you have those things that are worrying. That means that you may, if the system like that go into production, you may see CPU being low, everything looks healthy, but some user complain that things are really performing poor. You log in, you can't see anything. Very hard to spot, because you might be in the area where your transaction or your user may come in the area when these locks do not occur. So you need to be able to recreate that. So that's one example of unhealthy system. The other example that you may have a lot of variability between different transactions. That can be explained either because of the variability in the data, or some work that our users are performing. They might belong to the group that they have large data set associated with them than the other group, so then you can do a sensitivity analysis on where that is coming from. But introducing that might also be relevant. It's quite easy to spot when things like that happen, because we gradually increase the load, but things are not quite stable there. Also, another example there is trying to see how long the system will stay up. This example, this is a user load, so we gradually increased the user load up to a certain level, and then we kept it flat, so we kept it steady for a period of not even that long. That's just under an hour. And then what you can see is that the response time was quite stable up to a point, and then things start to go wrong. And the memory, that's memory there. So you can spot that this is not going to be a happy system. So that's even the simplest test will very often be enough to highlight that and show you that. Then you look at where it's coming from, try to fix that, and repeat. So now what I want to do next is just show you very briefly how what we've done so far, and how we take the approach, and what the process of generating those tests and how they run, and then we'll take some questions. So